Hello everyone, welcome to another webinar from our Rock in Action webinar series. My name is Leon White and I'm part of the Rock DM support team. Today we are going to make a short presentation about breakage and crushing and show how we can use Rocky to include those physics in our simulations. I hope you will enjoy. In different operations across many industrial applications, the breakage phenomenon can be present sometimes by design, in the case of comminution equipment, and sometimes as an unwanted effect that needs to be reduced or completely removed out of the process. When we are talking about breakage, we are considering the fragmentation of an initial single particle into multiple smaller pieces, ensuring that we preserve both the volume and the mass of the original particle. This phenomenon can occur when the particle undergoes a single high energy impact or compression, or repeatedly low energy impacts that can lead to particle damage or even after reaching the material stress limit during a deformation of a particle here. Rock simulation can bring some insight into such analysis due to the capability of real particle shape representation, and such a feature ensures that we can actually predict the loads applied to the particle and compute how the breakage will occur under a given conditions and under certain loads. This model can be used to predict fragment size distribution, the mass flow of the products, in the example here of a cone crusher. We can evaluate the power consumption required to break the particles, this roller crusher here for example, or even to identify where breakage is happening in equipment. We can evaluate in a certain chute where breakage is occurring, how to minimize such event. Now let's understand how breakage can be calculated inside Rocky. We are going to focus on the most common models that we have, which generate fragments based on the event that led to the breakage. Rocky has different approach for that, but in simple lines, all of them follow similar structure. So the first step is we need to characterize the material. We need to define parameters that define how brittle is the material that we want to interact with, how fine will be the fragments after the breakage, and this we need to be correctly defined in order to accurately predict and represent the real material. During our simulation, every particle in the domain will have their own strength calculated based on the material properties, particle size, and some probability functions that we have built in the breakage models. Once a particle undergoes an impact event or a compression, Rock will compute the energy applied to the particle. If this energy is larger than a certain threshold or a computed probability of breakage, the particle will break. And once that happens, Rock will compute the expected size distribution of the fragments and will decompose the original particle into smaller non-regular shapes, as we can see here in the video, ensuring that both the original mass and volume of the original particle is equal to the one of the fragments, and each fragment is their own particle. They have their own dynamics, their own properties, and can even undergo secondary breakage if the same conditions happen for the fragments again. In case that a particle do not break under a certain load, the particle can become weaker, or the threshold that leads to breakage can be reduced depending on the model that we select and the energy levels that were applied to this breakage, to this particle. Today we have a quick demonstration on how to set up and post-process a cone crusher simulation in Rock. I will show you how to set a cone crusher template motion, show the particle breakage parameters, a few best practices for brittle material setup, and for the post-processing, how to extract the power on the mantle of the cone crusher, and also evaluate and compare the original particle and the fragment size distribution. So this example here today is one of our actual workshops of a cone crusher. The reviewing the setup, everything here is a default force and the gravity in the minus y direction. The geometry is made up of a concave geometry, the cone or the mantle that really rotates around the shaft, the vertical shaft that eccentrically rotates in this chamber, and transmission axis in a housing that will define the chamber that is choke filled with particles using the circular inlet. So the first thing is to define the motion. The cone crusher has their own very common motion that we have a template for that in Rocky. So we can directly add a template of a cone crusher that needs to be defined with a pivot point and a rotation vertical axis that will define the direction of rotation of the assembly of the shaft and the cone with a certain rotational velocity and an initial orientation where this shaft is tilted around this vertical direction. Then we define once when the motion will start. This template generates two motions. One that should be applied to the shaft is just a vertical rotation around the given specified axis, and one for the cone or the mantle, which is a free body rotation around this eccentric shaft. So it's not only rotate with the shaft, but also it's free to rotate around. Since it's a free body motion, you need to correctly set up all the mass properties in order to properly calculate the free body rotation. Once you have that, we can check on the material properties, and it's very important to define a proper Young's modulus for the particles. Since they are undergoing high compression forces, if your material is too soft, they will undergo high overlap. So we can go as low as 5 per 8 Pascal, but recommended to use at least 1 per 9 Pascal. We need to define proper material interactions between particle, and boundary, and then the particle. Whenever we are dealing with breakage in Rocky, we need to use non-spherical particles. For example, here we are using the template of a polyhedron. The template can be played around to change aspect ratios, number of corners, so they can resemble your real particle. We are going to use random angles for injection, so they are not aligned in the chamber. And we need to define the original particle size distribution that we want to fit in the system. Then to enable breakage, just need to check enable breakage, select one of the available breakage models. Here we are going to use the ABT10, and we need to define how difficult it will be to break the particles, how fine will be the fragment distribution, and an energy-related threshold for the breakage. Regarding the fragments, we need to select one distribution model, normally the Gaussian-Schumann for the ABT10, and how small we want to compute the fragment. So the lower you go, the smaller will be the resolution of the smaller will be the size, but also the longest will be your computational time. We need to define the inputs or the mass flow of the particles in the chamber, ensuring that we always have a constant height of material at the entrance. Define how long we want to simulate this case, and very important, we need to define the starting time for the breakage. So the first is define when this breakage will start to be computed, and the delay after release means the initial time for breakage on individual particles. Once everything is set, we can hit start of your simulation. So talking about post-process in this case, here we have the already simulated result. We can see the original particles at the top and the fragments already calculated after the process or the comminution process. Let's start evaluating the mantle or the cone and extracting a curve of power. So you can right click and display the history of the power required to interact with the particles and the breakage of the particles just with the cone geometry. And we can transform this using the output tool to extract a single value by drag and drop the power into output. And let's say I want to evaluate the average power in a certain time. So I can select average, select a time range, And let's say I want to compute the average power between 5 to 10 seconds. And I have a single value represent this whole curve as an output that can even be sent to a design exploration or OpsLang or a simple report of those values. Now let's evaluate the particle size distribution. For that, I want to select two regions. And for that, I want to use a cylinder here to collect first particles only at the top or at the entrance. This will be my reference size distribution. I will duplicate this one and generate a second cylinder only to select the fragments that have been generated. As we can see, the particles are leaving the domain, but we have a very nice tool in Rocky that allows us to virtual compute properties of all the particles that cross this region throughout the simulation. So I don't need to store and collect all those particles. I will rename here just for cleanness of my post-processing, and now you use the so-called particle time selection. A particle time selection, I can select a domain, in our case a cylinder here, and virtually select all the particles using a certain time, or all the time, or a time range, or after a certain time. I will do this for both of my regions. On the top one, for all the simulation time, and for the bottom one, just after 5 seconds. And we'll see after Rock computes, I will have a virtual copy here displayed in red of all the particles that cross this region. Okay, so now I can measure a correct histogram of all the particle size that crossed both or were injected at the top and crossed the boundary at the bottom as fragments. So now I will create a new histogram, and I want to evaluate particle size. So we started with the fragments. I will drag and drop and select particle size. It will display me a histogram of the count, the number of fragments per size. I will just drag the same information from the feed of my material, but now I will tweak a little bit the histogram to show the correctly data that we want. We don't want the amount of particles, the count of particles. I want the total mass per size of material. And not only that, I want cumulative distribution and in percentage, right? So I can check those two values here. You can see that the histograms change. It's not that easy to see the distribution for the fragments yet. For that, I can set the range that I want to evaluate. So let's say from the minimum fragment size that I allowed to and the maximum size on my injection, and I can change the resolution and the number of bins. Now we can start to clearly see the distribution for the feed and for the products. I can make even finer resolution. And now I can clearly see in green the original distribution that was inputted based on the set of the particles and the resulting fragment distribution due to the process. And we can see the minimum size obtained from the original particle distribution here in green, and even the maximum fragment size is already smaller than the minimum fragment size. And this is the cumulative distribution generated by the breakage model in Rocky. So the results from such simulations can be critical for a comminution process evaluation. They can help you determine the best operating conditions like the speed, the cone or the mental position, setting the closed site settings and the open site settings, what's the feed rate for such operation, and compare the crushing power, the mass flow of products, and even stress over the surface of the geometries at each configuration. Also making it easy to compare different geometries and profiles, for example, of the concave and the mantle. Well, that's the end of our rock demonstration about breakage today. Now I would like to invite you all to attend our next 15 minutes webinars that will take place on the upcoming weekends. The next one will be on October 19th about rock customization. See you there, and thank you everyone for attending our today's session.